All right, so this is your stats sensei, Mr. Spensei, and we're going to continue on with the normal approximation of the binomial. Once again, this is all leading into running confidence intervals and hypothesis tests for proportions, which I don't think will be a big deal for you. Yes, the formulas have changed. There's a slightly different, well, there's a different condition, but otherwise the language is the same, and this follows our basic models. So first off, we need to note that the normal distribution is continuous as opposed to the binomial, which is discrete. In actuality, when we work with a number of people or animals, they're discrete. They really can be counted. However, the populations are large enough that the binomial becomes difficult and can exceed the limits of our calculator. Really isn't that big of a deal now, but when I was in school, it was a huge problem. So the normal approximation was very, very useful when we got to large samples. And it also becomes extraordinarily useful for hypothesis tests, confidence intervals, as you will see later on. So conditions. So how we need to make sure that we have a large enough sample. Well, how large is large enough? So, and this says population, this should say sample. How large of a sample? Well, the fact of the matter is NP and NQ must be greater than 10. And this varies from book to book, but this is the one that AP always accepts, and it's pretty standard. And please remember, Q equals 1 minus P, all right? So the number of failures has got to be greater than 10, and the number of successes must be greater than 10. So an archer with an 80% bullseye rate will be shooting 200 arrows. What are the mean and standard deviation of the number of bullseyes? Well, the expected value, this is the binomial because we have a fixed number of trials, we have a fixed probability, and we're hoping the probabilities doesn't change. So in this case, the expected value is always n times p. So in this case, 200 times 0.8 is 160. And on average, we'd expect her to hit the bullseye 160 times. The standard deviation would be NPQ, or please remember, the other way of expressing it, which is probably more correct, is NP times 1 minus P. But I already defined PQ as 1 minus P. Just makes it easier. So 200 times 0.8, and I get this value. So our standard deviation is 5.56. Is the normal approximation appropriate? Well, we're checking to see if the number of successes and the number of failures are greater than 10. Well, the number of successes, 200 times 0.8, oh, that's 160. That's definitely greater than 10. So that meets it. Probability of failure, please remember, this is just 1 minus the 0.8. 200 times 0.2, all right, is 40. That's greater than 10. Both conditions are met. We could use a normal approximation, all right? Here it just says use the empirical rule as to determine the number of bullseyes. Well, up above, we had our standard deviation. We said our standard deviation was 5.656. So one standard deviation, 160 plus 1 times that, because that's one standard deviation for 68%. 95% is 2 standard deviations, so 160 plus 2 times that. And then 99.71, this should say, of course, another typo. That should say 3 standard deviations, all right? So that gives us our values, all right? So we should be surprised if she made 140 bullseyes or less? Explain using the binomial and the normal. Well, let's look at the binomial. So 0, 1, 2, 3, dot, 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 139, 140, 141. And how many times did we shoot the arrow? We shot 200, so dot, 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 200. And so we made 140 or less. So I'm circling multiple values. So I would need to do a binomial CDF. So 200, choose 0. 0.8 to the 0, that's a probability of success with 0 successes. Probability of a failure, and we want all 200. And then I'm going to go up to 140 successes. When I do that, I can do that on a calculator. This would have been horrible back in my day, but our calculators have gotten much better. So the number of trials is 200. Probability of hitting the bullseye is 0.8. And we want 140 or less. So we're going to use our X value of 140. And I get 0.0004977. Pretty rare. Now, I'm going to use the normal approximation. By the way, this is more accurate than the normal. But what's a few thousandths among friends? We're getting really, really close. So in this case, we're going to go stat test, one proportion z test. Probability of hitting of a success is 0.8. Number of successes. All right. So when we're doing this, this is not finding exactly 140. It's finding 140 or less. So basically it's saying, hey, you shot. And in this case, our mean, what we expect is to hit it 160 times. We calculated that above. But we want to know the probability that we hit it 140 or less. So it's calculating that area. And we're saying it's approximately normal. So in this case, we want 140. Our sample size is 200. And we want to know the probability that it's less than. And we get 0.0002. Notice we're a good bit off, but tenths, hundredths, thousandths, 10 thousandths. So we're about 3 10,000ths off. And based on this, would I be surprised? And the answer is yeah. If she's really shooting 80%, for her to have 140 bullseyes or less would be pretty rare. All right. So the archer above purchased a new bow and hits 6 consecutive bullseyes. Is a normal approximation appropriate? Well, 6 consecutive. So we 6 times 0.8 is 4.8, less than 10. 6 times 0.2, not appropriate. Is this compelling evidence that the new bow has changed her bullseye rate? Well, first off, I can't choose the normal approximation. I'm going to have to go back to the binomial. And basically, we're going to say, what's the probability that if she shoots it 6 times, she has 6 bullseyes? When I do that, I end up getting 0.2621. So here's what that looks like. Oh, my little chart, 0, 1, 2, 3, 4, 5, 6. I shoot it 6 times, what's the probability I have exactly 6 successes? The second bars, binomial Cdf, trials, 6 trials, probability of success 0.8, X value 6. It's like, you know what? If she hits the bullseye 80% of the time, 26% of the time, you shoot it 6 times, you're going to hit it all 6 times. Not that rare. So I'm not convinced that the new bow has improved her rate. The same archer with a new bow hits at 55 bullseyes and 60. Well, how many shots would you expect to take to hit her first one? As soon as we say first, we're talking about a geometric, and I know that's not what we're talking about, but I just want to remind you. The expected value for a geometric is 1 over p. So her claim is 80%. So we'd expect her to hit it on 1.25. On average, we'd expect her to take 1.25 shots to hit the target. All right, that's on average. All right. Calculate the mean and the standard deviation for the above scenario. Well, expected value, 60 times 0.8, 48, NPQ, 3.09. Is a normal approximation appropriate here? Well, 60 times 0.8 is 48, that's greater than 10, and 60 times 0.2 equals 12, and that's also greater than 10. Conditions are met, normal approximation is acceptable. And she hits 55, and they want to know, is this compelling evidence? All right, so let's go back and try that. Now we can do this with a binomial, but I like to use the normal approximation. So we're going to go stat test, one proportion z test, and the probability of hitting a bullseye is 0.8. Our X value, we had 55, our sample size was 60. And what's the probability that you'd hit 55 or more bullseyes? And the answer is, well, that's 2 standard deviations. And by the way, I should have had the 2 in there. That's really important. So probability that Z is greater than 2.259 equals this. Given a success rate of 80%, there's only a 1.19% chance. It appears that her success rate may have changed. In other words, that's a pretty small p-value. And in this case, we would have said, hey, the null was, she hits it, or excuse me, P is 0.80. Alternative, P is greater than 0.80. It's like, yeah, it looks like it's changed. And it should have said has increased. All right, has increased, because change would be a not equal, but we should use increased. Current data indicates that 16% of teens who try marijuana will become addicted. 800 adults who use marijuana as teens were sampled. 165 of these adults were found to be addicted to marijuana. Explain why a normal approximation is appropriate. Well, once again, 800 times 0.16 is 128. 800 times 0.84 is 672. By the way, that's an accurate statistic. 16% indicate of teens who try marijuana do become addicted, or at least that is the current that is the current valuation. A lot of times it's expressed as 1 in 6. So 1 in 6 teens who try. So don't do it. So to calculate the mean and standard deviation of the distribution. You know what? While I'm on a soapbox, I'm going to go back to that 1 in 6. That's like playing Russian roulette, which is where you put a bullet in a gun and you spin the chamber and pull the trigger. There's a 1 in 6 chance you made a bad choice. So calculate the mean and standard deviation of the distribution. Well, the mean is NP. All right. NPQ is this. I'm not going to spend a whole lot of times. How many would you expect to have to survey to find the first? So 1 in 0.16 or 6.25. On average, we would expect to have to survey 6.25 adults who tried marijuana to find the first one who was an addict. So in other words, if you go, hey, consider randomly selecting 6 friends who use marijuana, then there's 1 in 6 of those will become addicted for life. Is this compelling evidence that the rate of addiction is different than previously believed? All right. And I need to pause for just a moment. Okay, so what I needed to check on is we had our sample size was 800, and we had 165 were found to be addicted. So we can do this using the binomial and the normal. So with the binomial, we go, what's the probability that we have 165 or more? And this is going to be a 1 minus a binomial CDF. Because essentially we're counting 165, 166. What's the probability of that or more? So, and because we're not starting at 0, and this will be our work shown, 800, choose 165. Probability of success is 16. Number of people who are addicted, 0.84. Probability of not being addicted, and we end up getting 800 minus 165 gives me 635. And then if we sample 800, what's the probability that all 800 are addicted, which would be this. So here we go, 1 minus second vars, binomial CDF trials 800, p-value 0.16, x value happened to be 165. Excuse me. We subtract out the highest one we don't want, so 164. And we end up getting 0.00003. Pretty small. When we go over to the normal approximation, by the way, this should be a greater than sign. What's the probability Z is greater than 165? And we need, and I was like, well, where did the 128 come from? And that's a good question because I'm not sure. And oh, so what we expected to have, we had 165. And what's the probability that we end up with 128? Well, the 128, see, I said that wrong, but the 128 came from this. If we have a 16%, of 800 is 128. So that's the number that we expect to have happen. All right. So looking at what's the probability that we'd have 165. And now we're not working with a proportion. We're actually working with actual values. So the second vars stat test, excuse me. Let's do a second vars. Norm CDF, lower bound 165, upper bound 99999, mean of 128, standard deviation of 10.37. And we end up with second vars norm CDF, sorry about that, 165, upper bound infinity 128, 10.37. And we end up getting 0.000179. So pretty small probability. Once again, not exactly the same, but we could run it as a norm CDF because we actually have mean values. All right. Now, and that's because we were looking, we didn't have a p hat. I mean, I guess we could have figured a p hat. So let's do a p hat. We can go p hat equals x divided by n. Well, p hat equals 165 divided by 800. So let's try that out. So stat test, one proportion z test, 0.8, x was 165, n was 800. Oops. And I have some sort of error here. It would help if I use the correct proportion. So our claim was 16%. We had a sample size 165, 800, and we want to know the probability. And when we do that, we end up getting 0.01797. And the reason that's important is because that's what we had here. So that was working it with means, but if we worked it with proportions, which I think is much easier, we would have said the probability that z is greater than, and then we'd have p hat minus p over p hat q hat n, or p q n, which in this case would be p hat is 0.2065. So there's 20% versus the 16% claim, and that's where we get our difference from. Sorry for the mistakes, but basically here's the deal. Either working with a mean or this are going to give you exactly the same. They are going to be different from the binomial. As we increase the sample size, the normal approximation becomes more and more accurate, but it's never exact. All right. So the big thing to take from this is NP and NQ must be large enough. They must be greater than or equal to 10. I appreciate you watching and apologize for the bumps in the road.